Our planet is not just a sphere of rock and water. One of the most crucial aspects of this system is Earth's magnetic field. This invisible force field surrounds our planet, acting as a shield against harmful radiation from the sun and deep space. Imagine a giant bar magnet embedded within the Earth, tilted slightly off-axis. It has two poles, north and south, which are not fixed points but rather areas where the magnetic field lines converge. These poles are not the same as the geographic poles, which mark the axis of Earth's rotation. The magnetic field is generated deep within Earth's core. This region, about 1,800 miles below the surface, is a churning ocean of molten iron and nickel. The constant movement of this liquid metal creates electric currents, which in turn generate the magnetic field. The magnetosphere deflects most of the sun's harmful radiation, preventing it from stripping away our atmosphere and harming life on Earth. To understand why the Earth's magnetic poles are moving, we need to journey to the heart of our planet. Deep below the Earth's crust, mantle and outer core lies the inner core. This solid sphere of iron and nickel experiences unimaginable pressure and heat. Temperatures here can reach a staggering 9,800 degrees Fahrenheit, hotter than the surface of the sun. Surrounding the inner core is the outer core. This region is also composed mostly of iron and nickel, but here, these metals exist in a liquid state. The extreme temperatures keep the outer core in a constant state of convective flow, much like a boiling pot of water. This churning motion is driven by the Earth's rotation and the transfer of heat from the inner core. The movement of the molten iron creates electric currents, which in turn generate the magnetic field. As the flow of this liquid metal changes, so too does the magnetic field. This constant shifting in the Earth's outer core means that the magnetic poles are never truly stationary. The Earth's surface, far above the tumultuous outer core, also plays a role in shaping the magnetic field. The Earth's crust is not a single solid shell. It's broken up into a mosaic of gigantic pieces called tectonic plates. These plates are in constant motion, albeit extremely slow motion, driven by the convection currents in the mantle beneath them. Tectonic plates converge, diverge, and slide past each other, causing earthquakes, volcanic eruptions, and the formation of mountain ranges. The Earth's crust and upper mantle contain magnetic minerals, remnants of ancient magnetic fields frozen in time. As the tectonic plates move, these magnetic minerals are carried along, subtly altering the local magnetic field. The movement of these plates, though gradual, contributes to the overall wander of the magnetic poles and the complex patterns of the magnetic field. While the influence of tectonic plates on the magnetic field is less dramatic than the churning of the outer core, it's another reminder that our planet is a dynamic system. The Earth's magnetic field is a result of the intricate interplay between the planet's molten core, its shifting tectonic plates, and the constant influence of the sun and cosmos. For centuries, the magnetic North Pole has been a point of fascination and practical importance. Explorers, navigators, and scientists have relied on it for direction finding and mapping the Earth. However, this magnetic landmark is far from stationary. It has been drifting, sometimes slowly, sometimes more rapidly, across the Canadian Arctic towards Russia. Throughout most of recorded history, the North Magnetic Pole meandered at a relatively leisurely pace, averaging about 10 kilometers per year. However, in recent decades, the pace has quickened considerably. Since the 1990s, the magnetic North Pole has been moving at an average speed of 55 kilometers per year. This rapid movement of the magnetic North Pole has practical implications. Navigation systems, especially those relying on magnetic compasses, need to be constantly updated to account for these shifts. The movement of the magnetic North Pole is a tangible reminder that our planet is not static. For centuries, the magnetic compass has been an indispensable tool for navigation, guiding sailors, explorers, and adventurers across vast oceans and uncharted territories. Even today, in our age of GPS and satellite navigation, the magnetic compass remains a vital backup system, especially in situations where electronic systems fail or are unavailable. However, the ongoing shift of the magnetic North Pole presents challenges for traditional magnetic navigation. A magnetic compass points towards magnetic north, not geographic north. The difference between these 2 points is called magnetic declination, and it varies depending on your location on Earth. The more the magnetic North Pole moves, the greater the change in magnetic declination over time. This means that navigators relying on magnetic compasses need to constantly update their declination values to ensure accurate navigation. Modern navigation systems, including GPS, are generally less affected by the movement of the magnetic North Pole. While technology has provided us with sophisticated navigation tools, understanding the Earth's magnetic field and its vagaries remains crucial for accurate navigation. The movement of the magnetic North Pole doesn't just affect those navigating above ground. It also has implications for activities that take place beneath the Earth's surface, particularly in industries like mining, drilling, and excavation. These industries often rely on magnetic surveys to map underground formations, locate resources, and ensure the safety of their operations. Magnetic surveys work by detecting variations in the Earth's magnetic field caused by different rock types and geological structures. Iron ore deposits, for example, can create significant magnetic anomalies. By mapping these anomalies, geologists and engineers can identify potential resource deposits, plan drilling operations, and assess the stability of underground tunnels and mines. However, the shifting magnetic North Pole introduces a level of complexity to these surveys. As the magnetic field changes, so too do the magnetic anomalies used to map underground formations. This means that magnetic surveys need to be periodically updated to account for the shifting magnetic landscape. The ongoing movement of the magnetic North Pole highlights the importance of accurate and up-to-date magnetic data for industries operating beneath the Earth's surface. The Earth's magnetic field is not just a phenomenon that affects human technology and exploration, it also plays a crucial role in the natural world, particularly for animals that rely on Earth's magnetic field for navigation and orientation. Birds, sea turtles, fish, and even some insects have an internal magnetic compass that allows them to sense the Earth's magnetic field and use it as a navigational aid. Migratory birds, for example, embark on incredible journeys across continents and oceans, often returning to the same breeding and wintering grounds year after year. While they use a variety of cues for navigation, including celestial patterns and landmarks, their magnetic sense is thought to be crucial for maintaining their course over long distances. Sea turtles hatch on beaches, then embark on long migrations across the ocean, only to return years later to the same beaches to lay their own eggs. This remarkable navigational feat is thought to be guided in part by their ability to sense the Earth's magnetic field. The ongoing movement of the magnetic North Pole poses challenges for animals that rely on magnetic navigation. While the exact mechanisms of animal magnetoreception are still being studied, it's clear that the Earth's magnetic field plays a vital role in the lives of many creatures. The Earth's magnetic field is not a constant. It fluctuates in strength and direction, and throughout Earth's history, it has even flipped completely, with the north and south magnetic poles swapping places. These magnetic reversals are not regular events like clockwork, they occur at irregular intervals, averaging about every 200,000 to 300,000 years. During a magnetic reversal, the Earth's magnetic field weakens significantly, and becomes much more complex, with multiple magnetic poles appearing in different locations. This weakened and chaotic magnetic field provides less protection from harmful radiation from the sun and deep space. Increased radiation exposure could disrupt satellite communications, damage power grids, and pose risks to astronauts in high-altitude flights. It could also have implications for the migratory patterns and survival of animals that rely on magnetic navigation. Some scientists believe that magnetic reversals might be linked to periods of increased volcanic activity or even minor climate fluctuations. While a magnetic reversal is not an imminent threat, the Earth's magnetic field has been weakening over the past few centuries. The Earth's magnetic field is an integral part of our planet, influencing everything from navigation and technology to the behavior of animals and the protection of life itself. The ongoing movement of the magnetic North Pole and the potential for a magnetic reversal highlight the dynamic nature of our planet and the importance of understanding these changes. Scientists continue to study the Earth's magnetic field, using a network of ground-based observatories, satellites, and sophisticated computer models. By monitoring the magnetic field's fluctuations and mapping its intricacies, researchers hope to gain a better understanding of the forces driving its movement and the potential consequences of a magnetic reversal. As our understanding of the Earth's magnetic field grows, so too does our ability to adapt to its changes. Navigation systems are being updated to account for the shifting magnetic poles. Industries reliant on magnetic surveys are developing new techniques to ensure accuracy. By studying and understanding these changes, we can better prepare for the future and ensure the continued well-being of our technological systems and the natural world that depends on them.